Hey everyone, it's Dr. Walker. This is video 57C, Calculations of Moments of Inertia. In this video, we're going to talk about how to find moments of inertia of continuous rigid objects. So these are objects that have a definite size and shape, unlike the ones in the previous video where it was just particles. The approach to this is the same as when we were calculating center of mass. If we have a continuous object, then what we do is we break it up into a whole bunch of little chunks, and each of these little chunks has a mass delta mi. And then all we do is we know that the moment of inertia is going to be the sum of the product of the r squared times the mass, right? The r's are the distances from the axis of rotation to each little mass. And then if we want to approximate the entire object, all we need to do is take the limit as the little masses become very, very, very tiny, as the size of the masses approaches 0, and then we have an integral. So very similar process to finding center of mass. The trick when solving these integrals is to be able to replace dm by something else that is easier to integrate over. So let's take a look at that. Let's look at mass density. You know, volume mass density is defined as mass per volume. If you have a volume here, it has a density rho, and you can look at a tiny little part of the volume and call it dV. So if you rearrange this equation here, and you solve for m, you get m equals rho v. So that means that if you're looking at a very, very small mass element, dm, that's going to equal to rho dv. That's the substitution that we're going to make in the previous integral when we're solving for moments of inertia and we have volumes. Now, sometimes we may have areas, so we make similar substitutions where sigma is the surface density, so sigma equals mass per area, and then we would make a substitution that the little mass element is equal to sigma d alpha. And if the object is just one-dimensional, right, so volume is 3D, area is your object is two-dimensional. What if your object is one-dimensional? Then it's along a line. Then we have to use the linear density lambda is mass per length. And then the little mass element dm is going to be equal to lambda dl. And we used this when we did a center of mass example, and I just explained it within the example. I didn't have a separate slide for it. On this slide, I have the moments of inertia of various rigid bodies, and rigid just means that they're not deforming as they're spinning. And all of these expressions can be derived by taking the integral that we just learned about. We will do a couple of examples in the next video, but I just wanted to show you that these expressions, they line up with what we've learned conceptually about moments of inertia. For instance, compare a solid disk right here to a thin spherical shell, which is a hollow disk. Compare these two. We learned that the object that has more mass distributed further away from the axis of rotation has a higher moment of inertia. As you can see, the moment of inertia of the thin cylindrical shell is indeed higher than that of a solid cylinder. So these expressions, they do make sense. You don't have to memorize them. You can always refer to this table in order to obtain them. Sometimes you need them for some problems. The last thing in this video is, what if we want to find the moment of inertia of an object, but it's not rotating about its central axis? The central axis is the axis that goes through the center of mass. In most of the shapes that we just saw, you could see that the axis went through that center. Now there was an exception here, and we'll actually derive this expression. But in all the other ones, the axis went through the center. So how do we obtain an expression when it doesn't go through the center? So what we do is we use the parallel axis theorem. If we want to find the moment of inertia about an axis that is parallel to the central axis, then we use the following equation. This new moment of inertia is going to equal the moment of inertia that goes through the center of mass plus md squared. M is the mass of the object, and d is the perpendicular distance between the axes. So we will also use this in an example, and it allows us to have a lot more flexibility when calculating moments of inertia.